This is my presentation on deep learning applications. The topic which I've selected is deep learning approaches in risk management. Jumping to the problem statement. Um, Financial organizations across the world currently are confronted with complex risk in a very dynamic business environment. And traditional risk frameworks, which rely primarily on historical data and statistical methods, often fail to capture the subtle patterns in large multidimensional data sets. This is where deep learning comes into the picture. It offers a transformative potential by leveraging the use of neural networks uh, to identify those previously undetectable patterns and improve on the predictive accuracy as well. So, this project essentially aims to evaluate and explore different deep learning approaches, focusing on the predictive accuracy of the models. Jumping to previous efforts, in 2017, J.P. Houghton demonstrated the use of a neural network model uh, in predicting market volatility, outperforming the traditional methods and approaches. In 2018, Justin Sirignaho applied various deep learning approaches to mortgage risk assessment, significantly improving default prediction. In 2020, Jintao Cao explored the use of an RNN for market risk prediction, focusing on sequential models to capture the temporal dependencies in financial time series data. More recently, in 2022, Howe developed a hybrid model combining a CNN and a LSTM architecture for credit risk assessment. Coming to my data set, so I'm utilizing a data set sourced from Kaggle. It's housed under the name of Home Credit Default Risk, licensed under Kaggle competition rules. It was the closest data set which I found to actual real world data. It's essentially a comprehensive collection of demographic, application, and bureau data. Uh, Specifically talking about details, it has about 300,000 rows, 122 columns, uh, with 106 being numerical columns and 16 being categorical columns. One key aspect of the data is that it's highly imbalanced, with 8% of the instances being only of one class, that is the default. Uh, Coming to my evaluation, so I'm going to be using two methods, two metrics, AUC and recall. AUC essentially because it's a classification exercise, and I want the model have to have the ability to distinguish between defaulters and non-defaulters. And recall essentially because I'm dealing with an imbalanced data set and I want to maximize the actual detection of defaulters for the model. Jumping to my first model, which is my naive model or a naive approach or the base or the standard model. So I'm basically using a logistic regression model, which has only been trained on the numerical features. I haven't applied any resampling technique or feature engineering, and it's giving me an AUC performance of about 62.7%, but the recall is significantly poor at 0. Coming to my traditional approach, so I started out with 5 models, and I found that a Random Forest and AdaBoost were the best performing models. And I used 4 advanced resampling techniques, out of which I found AdaSense and Smootian were the best performing ones. So I'm kind of pairing them together, model and resampling, and based on that, the best configuration which I'm getting is for add a boost with a Smoothine resampling technique. It's giving me an AUC of about 64.7%, with the recall jumping significantly by about 25%. For the deep learning approach, I started off with a standard NLP model with only one hidden layer. The performance wasn't improving as I increased the number of hidden layers, and even by tweaking the loss function. So I had to switch to a ResNet architecture, which was giving me a better performance. I even tried the performance with a sequence-based model, considering I had certain temporal data. But the performance wasn't a significant jump in comparison to the traditional approach. Um, and considering the computational power and the time it took for convergence. So for the sake of this presentation, I'm only going to be showing the ResNet architecture with oversampling and undersampling techniques. So with the oversampling technique, I'm using only one hidden layer, and I'm using focal loss as my loss function to prioritize on the minority class performance. So I'm getting an AUC of about 69.4% and a recall of about 43%. With the undersampling approach, I'm using a leaky ReLU as the activation function, and it's a balance set after the undersampling, and I'm using binary cross entropy as the loss function now, and it's giving me an AUC of about 70%, 70.7%, and a recall of about 45%. Uh, Jumping to the demo. So I'm using Streamlit here as for the UI as well as for the deployment. And essentially what I've done is I've taken one instance from the test case for my demo. Yeah, so what you see here is that the logistic model is predicting that this particular instance will be a non-defaulter. The traditional model is giving me the same target category. The deep learning oversampling approach has actually predicted this instance to be a defaulter. And the undersampling approach is also predicting this particular instance as a defaulter. It's possible for you to download the predictions as well, but this is just a demo of the models which are deployed on Streamlit. Coming to my results and conclusion, I kind of found that the advanced learning approach was definitely the better performing ones in comparison to the traditional approach. The key insights being that my dataset was highly imbalanced, so I had to apply resampling techniques. The deep learning approach outperformed traditional models, and I tailored different architectures using different loss functions as well for the minority class detection. And my ResNet architecture with undersampling was the best performing in terms of all the models. So my ethics statement, yes, all the financial data has been used responsibly, and I have not utilized any PII data, which is as per compliance. Thank you. This was my presentation.